Hi, good morning, Joy. So, uh, this is the class about operation research. So, can you tell me what did you learn in operation research one so that I can accommodate you with this course?
In Operation Research 1, we learn about the transportation, the salesman problem,
Okay,
and
TSP,
then
yeah.
we learn how to use software.
Oh, there's it. Hello?
Hello, can you hear me, sir? Wait, I'll change my Wi-Fi.
Okay. Oh, now can you talk again? Transportation problem, linear programming, is that, and then
Sensitivity analysis.
sensitivity analysis of the linear programming, and then
Yeah, then network modeling. Network.
network modeling is also there. Okay, so then I will know.
Yeah,
Okay,
and
and
I think that's it. We
that's
mostly
it.
learn about linear programming. Yeah, for half the semester.
Okay, good. So I will repeat a little bit on linear programming, and then I will go into the integer programming. Okay, so and then we go to dynamic programming. Okay, and what we will do. Okay, so here it is. I will share my screen. So you can follow this in the course syllabus. And this is my plan. So basically, you also decide what you want to learn. Okay, so if this is not enough or too much for you, you can tell me. Then we can or you want to learn something else, you tell me. Then we can change that. Okay. So as usual, this is the my number. I think you know already, right? And then you can contact me at any time using WhatsApp or uh, Facebook Messenger or email. Okay, and then you can also this is the course description. So uh, by the end of this course, you're supposed to be able to uh, do optimization modeling in decision making. So we will learn about decision analysis, game theory. Those are for decision. And then we will also learn about Markov chain, queuing theory, and I will add a few about maximum entropy. Last time we discussed last semester, I think, and ideal flow network. Okay, so the emphasis is actually to apply the operation research for a business setting as well as daily life problems. So okay, so the course objective. By the end of this course, I hope you can understand the characteristic of different type of decision-making environment and the appropriate decision-making approach, okay, tools. So there are many different tools for operation research. So I hope you can decide which tool you will use for which situation. That's the meaning of the first one. Second is, of course, you need to formulate, to build, and solve. This is just the computation. And the third one is to design a simple model to improve your decision making, okay, to develop your critical thinking, okay, and objective analysis for decision problems. So basically, we are talking about decision problems. Okay, and the last part is actually for your project. So you will do optimization you will use the optimization software. We can use Solver, but you can also propose something else. Suppose you want to use Python, or you want to use Minisync, for example, or MATLAB. Is up to you. Okay, so okay, this is what I suggest. So we will do a operation research introduction today, and then introduction to optimization. That means we will review the calculus, okay, and go deeper from there. And then I will review linear programming, and before I go to the integer programming, and then we go to dynamic programming. Okay. After that, we have a lot of discussion on decision analysis. You can also check this in the Lentera. Okay. So if you enter Lentera, here. So in this Lentera, this is the course syllabus today, right? So today we will discuss about introduction to OR. So the introduction optimization is basically calculus-based optimization, okay? And then I discuss about linear programming, integer programming. We already discussed last semester about knapsack and TSP. If you want, we can repeat again. If you don't, we just skip this. Okay, we can add something else. And dynamic programming, I think we need to deal with this. Okay, and then decision analysis. So you see a lot of materials on decision analysis. All of these are the slides already, so you can already study before the class. Huh? So until this is, and then after that we have midterm. Okay. After that we talk about game theory. So again, we have a lot of materials in game theory. And after game theory, we discuss about queuing theory. So actually, we have a lot of material in queuing theory. So I just put here 2, but depending on the time later, I can add more. Okay, and the last 3 is the Markov chain, maximum entropy, and so on. This is the last 3. Again, these are all the slides, so you can already study beforehand. Okay, next. So, is there anything you want to add or you want to remove? Is it okay? Have you ever learned about genetic algorithm?
I don't think so. Do you have an example?
Oh, it's an algorithm for optimization also, but using random values. Yeah, I have also the slide. If you want, we can insert in here.
I think it's nice to.
It's nice to
learn
have.
about
Okay,
that too,
so I
if
will
we have
add.
the time. Yeah.
I mean, when we add here, is also included in the exam, right? It's okay.
Yeah, it's okay.
Yeah. Okay, so I will add the GA. I don't know where to add that. Probably after the IFM. So GA, huh? What else do you want to add, or you want to remove something?
Markov chain is algebra, right?
No, Markov chain is a matrix for decision making. These are the foundation for the queuing theory and the ideal full network.
Okay, okay.
Okay. If you don't like it, you can read by yourself. I will not include. That is also fine.
No, no, it's okay.
It's okay. So I will include. Okay. So you can check my website as usual. Okay, and then the course, basically this is the Moodle of Petra. So last time we used Moodle. So this is the same. This is also Moodle, Lentera. So we will use this, right? The book, I can include this book in the Lentera if you want. Okay. So the main book is Taha. Okay. And then Hilary Berman is also another book. So especially for the integer programming and then queuing theory. Yeah, yeah, it's very good. Yeah. Okay, and then for the IFN, I can include also my book here. So those are the grading system is the usual. I think you already know. Okay, and here it is. Midterm is 20%. The course requirement. The final exam is 20%. Assignment is basically 30%, right? That will include the 25 plus 5 of recitation, and then the project is 30%. Is that okay with you, or you want to change this?
I'm okay with it.
Okay. So is that correct? 20, 20, 40. This is 30. Okay, so 100%. Now, the quiz is the usual. We use Fibonacci weight system, like the usual of my classes. Yeah, you already know. And recitation, okay, we will normalize at the end of the semester, and all the discussion will be posted online on YouTube, as the usual also. This one. Don't forget to claim your recitation, but please put the total cumulation of the cumulative recitation point on top, okay? So that I will not calculate all the point that you claim. Okay, you just put on the top, so I will just believe what you say. Okay, so submit in the Lentera right after the class. Do we have it in Lentera? The recitation? Not yet. Okay, I will add the recitation in this class. Next. Can you access the Lentera also? No problem.
Yeah, no problem. I'm currently a section.
Now for the project. Okay, well, the project is to analyze and to optimize real problem. So you can decide on your own what project you want to do for this. The purpose is decision analysis. That means you should be able to gather some data, okay, from any company or from any organization. That is fine. And then the purpose is for decision analysis, and then you can use any combination of these things that we learned in the class. So either queuing theory, probability game theory, linear programming, dynamic programming, and so on, right? So as much as possible, you use all. Okay, of course you cannot use all, but just as much as possible you use all. Okay, so for the project you need to collect data on your own, and then select a case study that you think it is okay. And you will formulate the optimization formula. You know, like in linear programming, objective function is what, the constraint is what. Okay. Of course, this is a project, 40% or 30%, so supposed to be quite big, right? Not just like example in the linear programming, right? It's much bigger than that. So, and then you will do you will analyze, and then solution. You can use any software, and then do sensitivity analysis, right? And then you compare, and then you will write a report. So that's the usual. And then you will define this in 3 workshops. Okay. Again, you can use any software tool, including spreadsheet. Okay. Next, our class have only 2 students, so only you and Leafy. Sorry. So then it's up to you. You want to group with Leafy or you want to do it separately. It's up to you. Okay, but please decide this week. Okay, so you discuss with Leafy whether you want to do separately or you want to do it together, and then you decide this week. Okay. For the midterm exam, again, I have a choice. So you can optionally take the midterm exam or create a paper, okay, based on that group project. Or we can also get the maximum between the two. Very flexible. Yeah. So this is the example of project. So for example, a queuing system, traffic system, okay, public transportation system, or financial system, banking, business inventory, or urban health, disaster management. It's up to you. You can decide what you want. Something that interests you. Okay? Something that probably useful for you. Okay, and reporting is multi-stage. So again you use Fibonacci with system. Okay, so you will write the staging report and then submit 1 day before the presentation. Okay, there are 4 stages. Yeah, of course you need to present your project. Okay, and then peer review if you decided separately, right? Now, what to report? Here, please mark your calendar. March 8th will be the project ideas. At this point, you're supposed to define your problem. Okay, so reporting will be March 7th, and then presentation is March 8th. At this point, I hope you have the optimization already done. So you will formulate the optimization part. And then what is the structure? You start to see the relationship between the part. Okay, is there any state or policy variables? Okay, and then what kind of policies you want to establish and so on. Okay, so we will evaluate based on the originality, attractiveness, merit, yeah? And then of course the relevancy to the course. Yeah? And I want to know whether you can finish the project on time, because sometimes the students make very big project that cannot finish. So I want to make sure that you can finish it on time. Okay. The second project presentation is in May 10. Reporting is May 9. That means you submit the report. At this point, I hope you already demonstrate the prototype of the application. Okay. In the report, you're supposed to have optimization formula, and then what is your plan for computation. Okay. So I expect that you have some kind of modeling decision and risk analysis at this point. Okay. So if you have some problems at this point, the limitation must be known. Right? The third presentation is in May 24, so very close to the third project presentation. Okay, at this point, you already validate and calibrate. That means you already do the computation. Okay, so in the report, I hope you can show the solution, the sensitivity analysis. You may ask, how about if you do all of this in the third project in the second one? Then it's fine. Right? Remember, the purpose of this staging is actually to make sure that your project become continuous improvement, so that you can revise early, okay, and to reduce the risk of unfinished project. Okay. So if you can finish everything faster than the usual, then this deadline, that is fine. Okay. So, and then the last part is, of course, June 7. This is nearly final exam. At this point, you don't need to present. You only write the report. Okay. So include in your report the software code if or Excel sheet that you use, software documentation, user documentation, analysis, okay, and the whole report. Okay. So, any question? Oh, Leafy is here already. Can you open your video, Leafy?
Sir, I have a question.
Oh, cool.
So, for example, my dad, he's working in the like operation department, right? So if I base
Use
my
that.
project from his
Yes,
data, is it fine?
that is not just fine. That is excellent.
Okay.
Right.
Okay, thank you, sir.
Right. In fact, it will give you better motivation, right? Right. That is better. Okay. But you need to ask your dad whether opening that data to public like this, because remember all your presentation will be posted in YouTube. So
Okay, yeah, I'll consult him about that.
next one. Okay, so final code and program specific must be submitted to Lentera, and they may be used also for the student next year. Right. So it's a bonus paper. Okay, so 5% of the project, or you can also ask to replace your midterm. Okay, but deadline submission is March 29. Okay, based on your project. You can only include my name if you think I have contribution. If no contribution, don't include. Okay. So this is the suggested format. Okay. And if you want to collaborate with me, please check this guideline. Okay. Okay, so the bonus will be based on not just your submission, but the acceptance within the before the end of the semester. That's why the deadline is March, so that you can submit it, and then by the end of the semester, will be able to be accepted. Just letter of acceptance is enough. No need to publish. Okay. So, as the usual in my classes, you can submit late if you want, okay, but don't go beyond the final exam date. Okay, if you submit late, minus 2% per day deduction. Okay, just by submitting your assignment and project reporting, usually you get 100 already. So better not submitting late. Okay, but after the final grade, okay, so you will have at least 48 hours before the final grade submission to the department. So usually after the final exam, give me several days. I will give you the your grade, right, in Excel. Then you can check, right? And after that, within 48 hours, please respond. Okay? After that, I will not change anymore. So that when we submit it to the department, I will not change. Okay. Okay, so who will put the attendance?
I can put the attendance.
Okay,
Just
so
the
I
two of
will
us.
I'll go to Petra system. It is in sync. I need to go out of this. How to go to Syllabus? Okay. Anyway, I will get the. Oh, okay. So NRP. Okay. After the class, I will assign you. Okay, so that you can fill in. What else? Next is okay, common ethic. Uh, Please attend all classes on time. Okay, if you don't be late. Okay, so open your video during the online class. Okay, and please study before the class. If you are offline class, of course, you please in the class don't eat and drink or smoke. No cell phone. Okay. No cheating is common ethic. No plagiarism. So, uh, look, when you cite somebody else's work or you use a formula or table or chart of other person, okay, or the text of other person, you can copy, no problem, okay, or quote of other people. So you can copy. There is no problem. But you just honor the other person's work by mentioning their name only, right? And then put in the reference. Okay? By not honoring others' work, you will be labeled as plagiarism. So that is a very big sin in academic work. Okay, so just honor other person's work. That is important. Okay. And for the test, we have no makeup test. That means if you don't join, uh, you cannot join anymore. Okay. But for the assignment and project, you can submit. I hope you can submit on time. If not, if you are late, you can submit late up to the date of the final exam. Okay, so I expect, as usual, your active participation and propose your ideas. Okay. Okay, for the project, what do you think? Livy, do you want to do it together with Joy or you want to do it separately? Or you need time to discuss later?
Maybe we will discuss it first.
Okay, you discuss later. Huh? So this is very nice course, only 2%, only 2 students, that is private. Almost private. Very nice. So, okay, so let's go to the first material. Is there any question or comment for the course syllabus or any change that you want? Do we have recording? Oh, yes. Can I pause a little bit? Okay, so let's start with our first material. You can also get it from Lentera. So Introduction to OR. Okay, so here it is. Right. So this is what we will discuss in this topic. Okay. So art and science of prediction, and then quantitative prediction with the 3 level of science. okay, model type and basis of model usefulness and caution in modeling. Right. So, there is a Danish proverb said that it's difficult to make prediction, especially about the future. Okay, it's irony. So, actually, we do make prediction in our daily life. Okay? Without realizing it, we already do a lot of prediction. For example, when you go to office or you go to your school in campus, for example, you already predicted the length of our morning commute, right? So when you shop from a supermarket and then you put your food in the refrigerator, so you already predicted the duration of your food, okay, in the ref, right? So same thing if you watch sporting events, like nowadays there is Olympic, Winter Olympic in Beijing, for example. So then you probably predicted the outcomes of the sporting events, right? The same thing, if you work, you will expect the salary increase next year, and so on, right? When you play stock market, you probably thinking about the direction. Oh, probably this stock will go up or go down, right? The same thing when you go out of your house, you probably think whether should you bring umbrella or not. That means will it rain later or not, right? So this is my first quantitative prediction. So this is the portrait of my grandmother. So I was about probably 7 years old at that time. Okay, so and as the usual, the Chinese tradition, okay, my grandma will ask, "Oh, when you work later, okay, will you give me some of your money?" She just joked like that. Okay, and at that point, I said to my grandmother, "I think when I work already, you already die, my grandma." Okay, so it was the talk of the small boy. Okay, and the problem is, it really happened. Okay, why? Because actually there is high probability that she will pass away when I was start working. Yeah, the fact is, she died when I was 20 years old. So how that the prediction happened? So at that time, my grandmother already 55 years old. Okay? My age was 7 years old. So I was thinking when I work probably around 22, okay, there's a 15 years in gap, and right. So between the present and the future time, I may have okay, there is no problem. The gap is about 15 years, right? So within that gap, okay, so 55 plus 15 is about 70, right? And then based on what I know at that time, the statistic, my friend told me that people usually die at 50. Okay, so 70 is beyond the age limit of the normal people at that time, right? So then that is the decision of the prediction. So in the past, okay, prediction has been associated with foretelling, right? Foreseeing, prophesying, divination, or soothsaying, okay, guessing. What is this? All about qualitative based on belief, right? Prognostication. So this is the past association of prediction. Okay? And the present association of prediction will be forecasting, estimation, Prediction itself, calculating, okay, anticipating, and projection. What is this? We are talking about more quantitative way, not just qualitative, right? Okay. And for the future association of prediction is based on conjecturing, okay, expectation, okay, proof, extrapolation, and likelihood. Okay. So when you see this, okay, the human knowledge in prediction has become better over time, okay, through quantitative prediction, right? So in the past, who does the prediction? Okay, the prophet, the wizard. Okay, they call it fortune teller, right? But present wizard is, of course, they call it marketer, right? Data scientist, statistician, modeler, or a weather forecaster, isn't it? So, and if you learn about prediction model, okay, including the OR, okay, basically you are a modern wizard, isn't it? So, how the prediction work? In the past, okay, when we want to create prediction, it's based on the power of God, magic, right? Now we predict based on mathematics, okay, statistics, right, science, and machine learning. So, in the past, it's based on belief, and right now we base it on scientific logic. Okay. So, in the past, okay, the science of prediction is an art, basically based on subjective knowledge of the person. Okay? While now, the science is relying on objective knowledge. It's so objective that we can actually put the science, the tools, into machine with this computer or calculator, isn't it? Right? So, in the past, it's really based on art with this individual perception, okay, unsystematic. But now we create the science of prediction, which is more systematic, rule-based. Okay, some procedure is there. So, what's the difference between art and science? Okay, again, art is subjective, okay, expression of creativity. Okay, it can be beautiful, aesthetic. It can provoke emotion or based on individual perception and experience. Okay, art usually unique, right? But science, in the other way around, okay, it must be objective. It's a system to acquire knowledge. Okay, it's about general truth about the general law, based on logic, right? Based on data, observation, experiment, or simulation. Okay, and it's not unique. Okay, it should be replicable. Okay, systematic. Okay, now let's enter the notion about quantitative prediction. Okay, so there's a quote by George Box here. Okay, this is the person who created Box and Jenkins model for the time series prediction. He said essentially all models are wrong, but some are useful. Okay, that is very true. Okay, so model is an abstraction of reality, okay? Simplification of reality. So it must be wrong because it's just a simplification, right? But some of them are useful. So for quantitative prediction, there are two ways. Okay? One way is called inductive approach, and the second way is called deductive approach, right? So in OR, we are dealing with deductive approach mostly. In machine learning, in statistics, we are dealing with inductive approach. Okay. In inductive approach, you have data. You start from data, okay, and you analyze the data, and then you generalize that data to create some kind of new paradigm, new insight, and theory. Okay. While in deductive approach, you start with theory. Okay? We start with some certain models, certain theories, certain principles, and then you create a prediction. And then your data is just to validate that prediction. So I give you example of deductive approach. Okay? You know the guy named Isaac Newton, right? So Isaac Newton make a prediction about the movement of heavenly bodies, the Earth, the moons, and the planetary system in the solar system. Okay, so of course the model originally comes from Kepler, but he put it into a new model of gravitational theory. Okay, based on that, actually we're supposed to be able to predict when, okay, certain planet will appear in our telescope at certain date. Okay, so then probably around 50 years later, okay, someone else using Newton model, okay, just based on 3 points, okay, 3 data points, okay, he predicted, he validated the prediction of Newton. So in using deductive approach, okay, you only need data to validate the prediction. Okay? While in inductive approach, you need big data, a lot of data. Okay. Now, in modern science, okay, these are the steps to create deductive approach. Okay, we start with what is called hypothesis, right? What is hypothesis? Guess, our guessing. Okay, and from hypothesis, we create what is called axioms. What is axiom? Axiom is basically our belief. Okay, something that we believe to be true, right? And then from the axioms, okay, we create proposition. So what is proposition? It's a statement that can be true or false, right? How do you create proposition? Proposition will be made, okay, by proving, okay, based on axioms or other proposition, right? And then from the proposition we create lemma, which is should be proved based on proposition, other lemma, or axioms. Okay. The same thing, from the lemma we create theorems, okay, which should be proved based on other theorem, lemma, proposition, or axioms. So basically the modern science is based on this kind of system that we prove based on the earlier proposition or lemma or axioms. Okay. So based on the theorem, we create what is called theory. Okay. So in science, theory is basically something that already proven. Okay. But if you read news or people nowadays talking in daily life, they said, "Oh, what you said is just theory." What they mean by theory is not the theory in science. What they mean by theory is just conjecture, hypothesis. So there is a gap of the language. The term theory in science is something that has been proven. But in everyday language, the theory means something that has not been proven. Okay? That's a very big difference. Science is also based on belief. Okay? So the belief in science, we call it axioms. So this is an example in the change in assumption. So, okay. Can you draw a line here? Can you annotate in this slide? Is it possible to annotate? Can you annotate? Okay, so that I will not show the person view how to make it. Can you annotate? Can you draw a line or a point? Can you share your screen or your whiteboard and then tell that this is a point? Is that a point, Joy?
Yeah, it's a point.
Livy, do you believe that is a point?
Yeah.
Yeah? How about a line? Livy, can you draw a line?
Okay. We will annotate.
Annotate that.
Okay.
Is that a line? Oh, not perfect, but
Wait.
Joy, is that correct line?
Yeah, it's a line.
Look, this is what you learn from high school, isn't it? Right? Oh, this is a point, this is a line. Okay, your teacher will draw like that. Now I'm telling you the truth. Okay? Are you ready? So there is no such things as point or line. Why? Okay? By definition, a line should be from infinite to infinite. So what you draw, you just draw is called line segment. Right? Line segment. So it's a finite. Right? There is a line segment, there is a length. The real line is infinite, from infinity to infinity, correct? You learned that also, right? Okay. The teacher told you that, but we still draw this way. Okay? So there is no such things. You cannot draw a line because it's infinite. Okay? The same thing with the point. There is no such things as a point. Okay? Why? Because point is zero dimension. What you draw here is probably a circle, not a point. Right? So it's a model. Okay? Point, line is a model. There is no such things. It's a simplification. It's not exist. Okay? But it's useful, right? Because of the point, because of the line, okay, we can create, we have a line here, right? So because of this line, we can create a whiteboard, we can create buildings, and so on. So they are useful, okay? But they are model, don't forget. There is no such things as a line or points. Can you understand what I mean by modeling here? Okay. Are they useful? Yes. Are they true value? No. There is no such thing as line. Okay. Right? Next. There is parallel line. Can you draw a parallel line? Can you draw a parallel line? What is parallel line? Parallel line is a line that never intersect to each other, correct? Correct? Yes. Parallel line is, so this is the concept which is called Euclidean geometry. In Euclidean geometry, which is 200 years before Christ, okay? Euclid proposed in the book of the Elements, okay? He said, look, there is a postulate, there is a axioms, okay, saying that parallel line does not intersect. It is true, that's by definition. Okay, that's the postulate. So what happened is there's actually axiom, that is actually a belief. Okay. In fact, parallel line intersect, isn't it? No? Argue with me. Does parallel line intersect? No. Oh, I will show you. I will show you that parallel line intersect. Okay. Can you see this? So the parallel line in projective geometry, okay, actually intersect in the infinite point, the vanishing point, right? So because of that, okay, you draw perspective, right? So when you draw perspective, you see the parallel line actually intersect in the infinite point. So because of this, okay, the whole assumption of Euclidean geometry is a failure, right? Then the mathematicians start to create a new theory. Okay, the new theory is called projective geometry. So remember, okay, the modern science based on proving. That proof, okay, is built up based on axioms, proposition, lemma, and theorem. Okay, so the weakest point of this is actually the axioms. Why? Because axioms is the assumption, something that you assume to be true. Okay, axiom is basically the religion of science. It is the belief, something that you believe to be true. Right? So that's why when you say you want to create a debate, you want to check the correctness of other persons, okay, what you will check? You check the assumption. Okay? Because when you check the proposition, then you can check the proof, right? If the proof is correct, then it's of course should be correct. But the weakest point of science is actually on the assumption. It is the axiom. Clear? Okay? So, now, in science, we have three levels. Okay? Three levels of science. So, I call this level 1, level 2, and level 3. So, my question is, which level are you? Right? So, I hope by learning this course, okay, you will be able to reach level 3. Okay? So, what is level 1? Understanding phenomena. Okay? Level 2 means you can already do prediction. Okay? Level 3, you can do optimization. Okay? So, let me go into the detail. So, I will put here the three levels of science. Okay? Understanding phenomena, prediction, and control as a function. Okay? Let me share this. Oh, I cannot remove the viewer screen. Anyway, okay, I will draw using whiteboard in that case. Okay. Let's say I will just make a simplification. This is not OR, but a simple statistic. Say I have an input. Okay. So let's call my input X. I have my output. Let's call my output Y. Okay. So, and then I have data points. Okay. Several data points here. Right? So, then what you will say? Oh, I create a model. Okay. That model is a function. Say this one. What is this model? I will say y equal mx plus c, right? It's a regression model. You learn this, right? So, this is my function. So, y is a function of x, right? And no, it's not just x. Huh? There is also a parameter here, right? So what is this parameter? I will call this alpha. Okay. What is alpha here? Alpha here is actually m comma c, right? What is m? M is the slope. Yeah, this is m, this is 1. What is c? C is actually the intercept, right? C. Okay. So I have this model. Okay. I have my data point, which is x, which is my input, and y is my output. Right? From my input and output, which is data, okay, and then I have my model. What is my model? F. Okay. And then I have parameter. What is my parameter? Alpha. Right? Look, my first step is understanding phenomena. What does that mean? Meaning, I have my data, input and output, x and y, right? And I have my model. Okay, so what happened is I changed my color to green so that you will see. I have my data, I input it into my model, right? And then from there, what I will do, I will get my parameter. Okay, from my data, x and y, which is input and output, right? I input it into my model, and then I will get my parameter. Okay, in this case, alpha. What is alpha? Again, it's the slope and the intercept, yeah, MC here. Is it clear? This is my first step. So this is understanding phenomena, right? Based on this, what will happen? I will have this line, correct? Because of that data, because I know the alpha, and then I will have this line. Correct. Okay? So if I have this line, that is the first step, understanding phenomena. Okay? Why? Because now I understand this is the model that I want to use. Okay. The second step is prediction, right? What does that prediction mean? Well, prediction mean, second, right? In the prediction, what I have my data, but not all data. I have only the input of the data, which is x. Oh, what happened? Sorry. This is very bad system in the class. Wait a minute. Can you still see me?
Yeah, we can.
Okay, so then probably okay. The second step is you have the data, okay, and use that first step model, which is the F that you have, and then you also use the calibrated parameter that you have, right? Then what you will get from here? Easy, right? What you will get is your output. This is what is called prediction, right? Prediction means you have the input of your data or new data, okay? Not necessarily the same data as earlier, okay? And then you have your model, okay? Any model, and that's why I put it F here. Okay? In this example, I put it linear model, but not necessarily. Later on, we will not use linear model, right? But this is just example, okay? And then what happened? You calibrate it, right? You get the alpha here, the parameter. Okay. From there, you predict the y. Clear, yeah? So once you already know the model, that is the first step. The second step is to predict. Once you know how to predict already, you go to the third step. What is the third step? To control. Okay? What does the control mean? To control mean you have a target. You have the goal. You have the result that you want. You have desired output. Okay? And then what you will do? Okay? You have desired output. Okay, number 3. So I will put number 3 here. Okay? What you have? You have your goal. Okay? Your output, right? Your purpose. And of course, you will use the first step. A while ago, you have the model that you are already using, and you already have the alpha that you already calibrated, right? But this is not just the usual model. Why? Because this is supposed to be the inverse model. Okay? From there, what you will get? From there, you will get the input, right, of your data. So that means if I know my goal, if I know my purpose, okay, optimization means I want to know, okay, what change I should do to my input in such a way so that, okay, I can, using this change, I can reach my goal. So given the objective, the Y here is the objective, right? And certain constraint that you have, right? Then you want to know the input. Is this clear or not? So do you understand the meaning of optimization here? Why is it important? Right? Because in prediction, you already know, okay, I know the input, I know the model, I just input this, I just plug in this value of the input into the model, I get the prediction. Simple. Right? But in optimization, no, you need to get the inverse function. Okay? The whole OR course, operation research course, is about this number 3, isn't it? Okay? So you have the target, okay? You have the objective. Okay? Then you want to know the input. Okay, up to here, is there any question? Okay, let's go to the slide. Okay, you see here? Okay. In understanding phenomena, I have X and Y and the model F. Okay, I will get the alpha. Right? And then in prediction, I will have the X and alpha and F to get the Y. Okay? In optimization or control, I will have the inverse function and the Y and the alpha to get the X back. Clear, yeah? So, in level 1, understanding phenomena, you will ask, what is that? Why this happen? How does it work, right? So, start to create model. In level 2, prediction, you start to ask, what will happen if we change this? What if I do this, I do that, okay? How sensitive it is, right? In level 3, you have the goal, okay? How to achieve that goal? How to change, what to change so that I can get my desired output? How to minimize my cost? how to maximize my profit. Right? So this is level 3. It's not easy, of course, right? Because you are in the highest level of science. Okay? At the same time, this is exciting. Okay? Now, I want to show you here is the invariance. In this slide, I want to show you the invariance. Look at this. In level 1, you have one invariant. What is this? The invariant is the model. You don't change the model. Okay? Meaning, you decide the model and you assume that model is true. Again, this is the axiom. Remember earlier I said the axiom is the weakest point. So if your assumption is wrong, then everything is wrong, collapse. Right? So remember in level 1, you assume your model. That is the things that does not change. That is the invariance. Right? Variance means change. Right? So invariance means don't change. Okay? Again, the arrow here represents, look, this is the input, this is the output as the arrow to this level 1. The output will be the parameter. Clear, yeah? Level 2. In level 2, there are 2 invariants. What is this? The model, then the parameters. Why invariant is very important? Because this is the assumption. Okay? You cannot make prediction if you don't make this invariant. Right? What is the meaning of this invariant of the parameter? That means the past predict the future. The previous data predict the next data. That's why the parameter does not change. Right? Is it clear? So the parameter is invariant. That means the past predict the future. Okay? The old data predict the new data. Without this invariant, you cannot predict. This is the core of wizard, right? You want to become modern wizard, right? You want to predict something. So don't tell me, oh wow, you can predict something awesome. No. Once you learn the real prediction, mean there is nothing awesome there because you already assume something there. What do you assume? The model, the parameters. Yeah. Okay. Next, how about level 3? Again, the same. Okay. You assume the inverse model and the parameters. Right? Your input is the output is the input. Right? It's reversed. But this is big assumption here. Unlike the second level earlier, okay? Model here is basically function, right? But in here, the third, look, you assume is not the model itself, but the model inverse. That is also make assumption that the model inverse exists, which is not always true. Okay, so how about if I make a model of prediction and then I cannot find the inverse function? Okay, if I cannot make the inverse function, then you cannot do optimization using that model. Because inverse function does not necessarily exist. Oh, is it difficult? What did you learn? Okay, I want you to give me your feedback. What did you learn today? This is like the essence of the whole semester, you know. But, right? I try to abstract that into very simple, just a function. So, which level are you? Are you level 1, level 2, level 3?
Since you're doing operation research, so we are at level 3.
Right,
But
you're supposed to be in level 3, right?
yeah,
But this is like the highest. So, uh, you after this, you can talk to anybody, okay? Say you talk in, especially somebody in social science, okay? In culture, for example, in history, for example. And then you will talk to them. They will say in history, okay? They will talk about history in the past, right? They will describe the history very nice. Then you ask them, can you predict something based on what you describe? What is the meaning of that? You want to test them if they can go to the level 2, right? Then they say, of course cannot, right? Then they said cannot, that means, okay, your knowledge is level 1, I know you, right? Okay? If they cannot predict, don't ask them the level 3. Can you control that? No way, right? Do you understand the meaning of control? Say, you have a society, you want to control the society. You have a company, you want to control the company, right? You want to manage it. If you cannot do the prediction, then there is no way you can do control, right? Why? Because in level 2, you need to create the function and the prediction, right? And then level 3, you need to make the inverse function. Is it clear now? So once you talk to somebody else, then you start to realize, oh, where you are, right? So, okay. How about this? Okay, how if I don't have the knowledge, okay? I don't have the data, okay? I want to make a decision, right? About something, okay? But I don't know the knowledge. I don't have the data. Can I still make a decision, right? The answer is yes, okay? So in fact, that is proposed by Pierre Simon Laplace, yeah? 17th, 18th centuries, right? So that's why we call this invariant principle. What? Laplace principle of insufficient reason. Okay, we will use this in decision making later. Okay, what it say? It say that in absence of any other knowledge, okay, all hypotheses are equally probable. What does it mean? If I don't know the distribution, I will assume to be uniform distribution, not normal distribution, uniform distribution. Okay? If I don't know anything, I will just assume they are equal. In fact, that's what happened. Say you have a coin, okay? You want to toss a coin, right? Then you will say, okay, that is 50-50. See? Equal. Right? Okay. You have a dice, okay? You don't know anything about this dice. Then you assume, oh, this is a fair dice. Then the probability is 1/6, right? How do you get 1/6? That is the assumption. How do you base the assumption? Laplace principle of insufficient reason. Okay. Okay. With that, then you can start to make a decision based on certain threshold. Right. So here is a modeling as a transformation. What does it mean? You have a real world situation, okay? And then you're supposed to create a real world solution, isn't it? Right? A real world situation, then intuitively you make a decision as the solution for the real world. What will happen if you do that? You will do a trial and error in the real world, isn't it? Right? Say, government usually is doing this. Oh, I want to experiment in the road, and they will widen the road. Okay, they will create this and that. Okay, they will create a policy. Okay? Without doing experiment in the model. What will happen? Many people affected. Many budget has been spent, and then it's actually a failure project. Okay? Even if you increase the number of the lane, the number of lane width in the road become bigger, you demolish the houses, but still traffic congestion happen, right? Yeah? So the problem happened because they have power, okay, they have budget, it is not their own, right? And they use it for the real world solution using experimentation directly in the real world. So this is no, no, no. Okay. If it is your own money, it is your own company, will you do that? No way, right? Okay. That's why usually private companies will not do that. Why? Oh, they will do a model first. Then they will try to solve the experiment. They will do optimization in the model first rather than in the real world. It's cheaper, right? It's much cheaper to do experiment in the computer rather than to do it in the real world. And faster also. Okay? For doing that, you need to assume. For doing that, you need to model. Right? Of course, you need to learn modeling. Okay? Then you get the solution in the model, then you apply that in the real world. Faster, cheaper, okay? Much better. And you will get the optimization. Okay? That's why we do modeling. Okay? That's why we don't do directly experimentation in the real world. Is that clear? Okay, so this is just the same as before, the three things that I explained about it. Okay, so in the level 1 description of phenomena, okay, you have the function variables and you learn the alpha, which is based on the past and current, right? So the second part is the prediction of the future phenomena, which is based on the past and current. Okay. Again, you assume alpha does not change, the model also does not change. Okay. And the third one, the third level of control optimization, okay, again, you base it on the current or future. The current or the future based on the past and the current. Okay. Again, you cannot predict out of nothing. Yeah. So there must be based on certain things that you assume to be invariants. Okay. Once you know this, everything is fine. So don't forget, you need to mention what is your assumption so that people will not think that you are doing magic. Okay, so that is the difference between science and the prophet, right? Okay, so in description of phenomena, okay, you start to model, okay, then how to model? You simplify, okay, the principle of parsimony, okay, which is to exclude the irrelevant, okay. If you have familiar concept, you have a form or procedure, you just use this. Okay. And then in the second principle is try to think in terms of perspective. Okay, what is the relative importance of various model characteristic? What they do? Okay, what they do not affect. So you start to think in terms of part of the system. Okay, so say for example you want to model a road. Okay, in the road there is, you probably want to simplify. Oh, in the road probably have vehicles, right? Have the road itself, the width, and so on. Right? But along the road there is also electricity line, yeah? The internet line, right? Will you include or exclude depending on your purpose, right? In the road probably there is some ant, there is some rat there, right? There are some bird. Will you include? Probably you will not include. Okay? You simplify, you will exclude the irrelevant to your purpose. Is it clear? Okay? So you don't put everything in your model. Okay? Only put things that is relevant and simple based on your purpose. Okay. Now, when you do prediction, second level, okay, you extract the maximum relevant information from the history, from the past, okay, to learn about the future. Then the question is what change or intervention, okay, action to be done in the system. Okay. So if you want to create a real prediction, you need to put into the quantified level. The form still the same, the concept still the same, but you need to put it into quantified level. Okay. Now the third one is control, right? The optimization. In this case, you want to influence the behavior of the system, right? So, of course, you know that some certain aspect of the system cannot be controlled. For example, a farmer is affected by the weather, right? So, of course, the farmer cannot control the weather, right? So, but the farmer can control the decision what to plant based on the weather, right? So, there are certain things you cannot control things, but you can change your policy. Okay? So try to investigate the robustness of the system. Okay, in this case based on elasticity or sensitivity of each component in the model. Okay, up to here, right? Is there any question first before I go to the next topic? Is it clear? The three types of level, the three level of science. Okay, understanding phenomena, prediction, control or optimization. Okay. The next topic is rather light, so it's model type. Okay. I said all the time, we are what we model in our mind. Okay. So basically, we always model everything in our mind, which is called mental model. Okay, so model can have many forms. Okay? It can serve many purposes. Okay? There are two types of model. One is physical. Okay, the second is symbolic or abstract. Okay, so scale model, 3D print, right? It's a 3D physical object that look like exactly the same like the actual one, but the size is smaller. So this is useful. For example, for aerodynamic in the airplane, right? By employing this model, scale model, okay, we check the wind tunnel, for example. Okay, in the wind tunnel, so what is the stability of the model? So, for example, the building or the aircraft, okay, can they withstand? The same scale model they will put into the vibration, for example. Okay, at what level they will collapse. Okay, so the scale model usually expensive to build, but with the 3D printer usually now become easier to create the scale model nowadays. So uh, the problem with the scale model is it does not generally lend itself to systematic optimization. So you will create a lot of scale, okay, scaling different scale so that you will get useful optimization, but that's very expensive. Okay. So in this case, a scale model or physical model is basically more on evaluation tool rather than for optimization, right? Then we go to the second type of model, which is abstract, symbolic. Okay. So mathematical model or simulation belong to this broad class of abstract model. What is this? Anything, okay? Any set of rule, any set of relationship that describe something, that is a model of that things. Okay, so this include, look, okay, this include your mental image. Can you imagine something that is mental model? That is a model, right? When you look at a novel, for example, oh, the rules, the law, law is actually legal code, right? It's actually an abstract model, right? A novel, stories, is an abstract model. Okay, so when I said abstract model here, it's quite broad, isn't it? Not just a mathematical model, right? So one thing that we always use in our mind is called mental model. Okay, our mental model process based on concept, based on knowledge that we have learned, right? Based on the culture that we have, then we make decision based on our mental model. Okay, look, in reality, okay, what we have in our mind, this concept, okay, our mental model is not the fact. They are model in our mind. Okay? Sometimes we don't realize it because we think this is real. Okay? As simple to children play with toy, right? And they imagine something. Okay? So, mental model, okay, our mental concept are abstraction based on our experience, based on our education, based on our purpose and context. Okay? This experience has been filtered, okay? Has been modified by our perception, sometimes by organizational process, such as the culture, education. Okay? Our parents shape us, isn't it? Right? So then we produce our mental model, how we see the world. Okay? That's why there are some people become religious fanatic, become terrorists, for example. Right? Why? Because their mental model changed, okay, based on education. Then they filter everything already, that only what they want, what they are educated, that is the one that they will think that way. Why? Again, based on mental model. Very dangerous. Can be. Eh? So, this is the characteristic of mental model. Okay? Mental model are stable, overly simplified. When something happen, contradict our mental model, okay, we tend to dismiss. Okay? What happened is not, we don't want to modify our belief. Okay? We don't want to modify our attitude, right? We don't want to modify our opinion or prejudice against others or against things. So when we deal with something so complex, right? We confuse and then tend to be dogmatic, isn't it? Right? Yeah? We don't want to change. Okay? This is the characteristic of mental model. But we need mental model to think. Okay? So, therefore, all our thinking really depends on model. This is our main model that we have, that we use. Okay? And we will compare this. Our model, mathematical model, will compare with mental model. Huh? So, we know that our mental model is ill-defined. Why? Because it keeps changing our assumption, actually. We keep changing our purpose without realizing it. Very funny. Human being is very funny because of this. Right? Okay? The problem is our assumption keep changing and not clearly identified. Okay? Oh, I know it. Okay? But I cannot express it. So it's not easy to communicate what I mean by that. That is a mental model. Okay? And not only that, it's difficult to manipulate. Okay? Effectively. Better than mental model, of course, pictorial model. So we create a photo, a chart, a sketch, right? So we create some kind of aerial photograph like this. And then we do a topographic map, right? Then we can see big picture, right? So you have a map. Okay? Because of your map, you know that there is some shop there, okay, 1 kilometer ahead of us, even though you never been here before. Amazing, right? For the people who does not know map, you are amazing. You can predict that there is a shop nearby here, right? 1 kilometer from this place. How do you know that that is a restaurant? How do you know that that is a noodle shop? Well, it's a Google map. Right? You have a map. But people who does not know the map, they will think that you are amazing. How can you are a wizard? You know. Have you been here before? No, you never been. This is my first time. But you have a map. Amazing. Right. Yeah, sometimes you don't realize that you are amazing using the map, right? Because you are already used to, right? So, the same thing with diagrams, right? Using diagram is a special type of picture model that you can see the interrelationship among the components. Okay, you can start to see the input flow to the output. You can start to see the sequence of the timings, of the activities, of the logical steps, right? So then you start to draw diagrams. Okay, there are standard diagrams called UML, right? Did you learn that? Okay. If not, please learn about UML, huh? Unified Modeling Language. Okay. This is a standard diagrams. Okay. Next, diagram alone cannot be used for optimization. Okay. Well, yes, we can do decision analysis, but that's not diagram alone, isn't it? Right? You still do the optimization based on the mathematical analysis, right? Then we go, the next is matrix, table. Okay? This is again common model for decision analysis that can be used for optimization. In this case, right? The most powerful, okay, abstract model is called mathematics. Okay? Why? Because mathematics is very flexible, abstract language. Okay. I went to Japan first time in 1990s, right? And I need to read a lot of Japanese paper, right? Which I don't know the language. I don't understand at all. But I can see the mathematics in the paper. And based on that mathematics alone, I can build the code. I can create a model. Even though I don't understand the paper. At that time, we have no OCR, okay? So we cannot translate directly. So nowadays, it's no problem. You just use the OCR, you can scan, you can get the language. In 1990s, there is now nothing like that. Okay, so using mathematics is universal language, meaning that you can actually use the same language all over the world. Okay, so I see this mathematics as a language. Okay, and in mathematics, if you look at it, actually very simple. Okay, what? It's just variables, okay, parameters, functions, okay, that relate that variables to the parameters. Right. Okay, relation between one and the others. It is very powerful, well used, but because of the power, it can be abused also. It can mislead many people, okay, depending on the objective and system view. So when you said, oh, I'm using mathematics, you can doctorate your model, then you can tell lie based on the mathematics and statistics. So that is abuse of the system. Okay. So the most important mathematics is actually the one sign. What is that? Equal. Equal sign. Okay. So based on equal sign, we have what is called equation. You see, equal equation, right? Because of the equal sign. So you have revenue equal to productivity times price, profit equal to revenue minus cost. So these are the common sense equation that you can put. But there are some empirical based equation, which is sometimes not really common sense, but when we put it together, for example, sales is a function of GNP and price and advertising expenditure, competitor, and so on. Okay, these are based on empirical, meaning what? Based on the data that you have, and then you do some kind of statistical modeling, machine learning. Okay, you can get this model, okay, which sometimes based on correlation rather than causation. Okay, now this is important. When you create a model later, okay, you need to judge your model based on usefulness. Okay? Yes, model validity matters, okay, but the most important is the usefulness of the mathematical or the simulation model. Okay? How do you judge? You judge it based on the comparison with mental image or other abstract model. Okay? So think about it in terms of clarity. Okay? Is the structure clear? Is the underlying assumption clearly stated? Is the consequence clear? Okay. So this is the quote by J. Forrester. So J. Forrester is the father of system dynamics from MIT in 1960. Okay. He said, by constructing a formal model, our mental image of the system clearly exposed. General statements such as size, magnitude, influence are given numerical values. As soon as the model is so precisely stated, one usually asks how he knows that the model is right. A controversy often develops over whether or not reality is exactly presented in the model. But such question means the very first purpose of the model, which is to be clear, to provide concrete statement that easily be communicated. So you see here, based on this quote, that the purpose of the model, okay, is for communication, right? So people always ask, but that is not represent reality. we can never prove that any model is exact representation of the reality. In fact, it's not. Okay, so the model should not be judged on the absolute scale to condemn them for failure to be perfect, but on the relative scale that approve them if they are actually succeed in two things: clarifying our knowledge and to provide our insight about the system. Okay, so one day you will present your model to not just to me but to everybody else, right? Correct? And then people will ask you this question, right? Correct? When you present your model to someone, say you are in the government or you're in the company, okay? Even to your own father, for example. So you presented your model and then they will say, oh, that is not reality. Then you know the answer. Okay? I already tell you the answer here, right? Don't just turn based on the absolute scale that this is the reality. Okay? In fact, there is none. Okay? But whether we clarify our knowledge, whether we provide insight about the system, that is the purpose of modeling. Okay? So when the model is reduced to diagram, to equation, when the assumption is examined, when we can communicate with others, right? When we can compute the time pattern to determine the behavior based on the model, then we hope we reach level 1 to understand the reality better. That's it. Okay? Okay? At least you can do level 1. So, okay. Now, the purpose of data, okay, two things. One is to validate the model. Second is to calibrate the model. Okay? Don't think that based on your data you can solve the problem. That is the wrong way of thinking. Okay? So, in model calibration, what is model calibration? It's a process to determine the parameter. Remember earlier, level 1. Okay, you have the input, you have the output, you have the model, you get the parameter alpha. So this is called model calibration. So you fit the data into the model. Okay. The second is called model validation. What's the difference? Validation is a process to test the fitness of your calibrated model. That means your model is already calibrated. Okay? And then you use different data that you use for calibration. So I will draw in the whiteboard. Okay, I clean this one. Okay. Suppose this is your data, the whole data set. Yeah? The length represents the data set. Okay. So what you will do is you don't use the whole data, okay, to calibrate your model. So for example, you just use half. Okay. This part of the data, you put it into the model. Okay. So this is your X and Y. Your X and Y. Okay. So your X and Y here, you put it into the F, you get the alpha, isn't it? That is called calibration. Okay. How about validation? The validation process, okay, you use other data here. Okay. You already have this model, right? So you use this. Oh, I have the X here. Look, I have the X2, Y2 here. I have X2. I also have Y2, right? But I don't show it. Okay, I put input here, X2 into the F and alpha. Okay, X2, comma alpha. Okay, and what I will get the Y. Y estimate of 2, right? That is the prediction. Okay, In validation, you do a prediction. Okay, and then you said, oh, I will compare with the original Y2, larger, smaller, or equal, right? Oh, mostly equal. Then the model is valid. Okay. When you said, oh, I have new the prediction of this based on the old data. Okay. They are not equal. They are very far away. Then yes, you have calibrated your model, but your model is not valid. Why? Because it can valid only within your data that you calibrated, but cannot be used for other data. Clear? Do you understand the meaning of validation? In validation, okay, you predict based on the new data. Okay. We just already have the output, the Y2 here. Okay. And then you compare. What is the error? Okay. If the error is very big, that means not valid. If the error is small, okay, valid. Okay. Is it clear? Good. Okay. Next is model verification. Look, step 1, step 2, model calibration, model calibration, model validation, you can use computer. Right. Okay, you just input the model, you run the program, it run for you. And then we'll give you accuracy, how many percent. Okay. But this one, model verification, is the one that make you human. Say you have AI, can do all of this model validation and calibration. The AI cannot do model verification. It is you, human, who's supposed to do this model verification. What is this model verification? Okay. This is the one that you interpret. Okay. Whether your model is right or wrong, you interpret it. Okay. Whether the sign is right or wrong. What is the meaning of this parameter? So this, you as the human being is the one who interprets that model. Yeah? Computer can only do the first step, the second step, yeah, which is the calibration and validation, but model verification should be you, human being. Okay. We have only 4 minutes. Do you want to stop here first before going to the next? We will come back again 1 o'clock, right? For the next.
Yeah, we can meet again at 1 o'clock.
Okay, so let's have a lunch first then.
Okay, thank you, sir. See you at 1.
See you. I will close this recording then. Okay, let's resume our class again. Thank you for the lunchtime. Right. Okay, where is so stigma means curse. Okay, so I want to discuss about the caution so that we can say, look, if we are not cautious enough about prediction, okay, these are the possibility that you need to think about. Okay. So, in the past, when you predict something and it's wrong, that is fine, right? But now, in modeling, okay, we use quantitative methods, so it's becoming more precise. Then you need to always check the units, okay, and dimension. Okay. So especially if you have equation, that means the left hand side and right hand side should be the same dimension and the units. Okay. So for example, when I said unit, it means the meter, okay, kilograms, seconds, for example. Yeah. So the dimensions of meter is length, right? The dimension of kilogram is mass. The dimension of seconds is time. So it's not only the dimension must be correct, but also the unit must be correct. Yeah? So we have what is called GIGO, garbage in, garbage out. That means when your input is inaccurate, then it will not magically create accurate result, right? So in that case, your input data must be accurate enough, should be clean enough. And remember, data cannot be used to solve the problem. The same thing with model. Model also cannot be used to solve the problem by itself. You still need to interpret. It's human who make the decision. Okay. Don't expect the machine can do all things. Okay. So the mathematical relationship is not the solution by itself. So we can say these are the possible solution, these are the alternative, and then this is the decision. But remember, whatever the decision made by the tools is just a suggestion. Okay? It is you who decide to accept that suggestion or not. Okay? Of course, they are very nice suggestion, but it is you who still should decide as a human being. Okay? Don't expect the machine to make decision for you. Okay. Now, often happen that none of this mathematical or simulation solution makes sense. Okay. So, in that case, you start to consider, oh, maybe some of my assumption is not correct. Okay. And if your problem is complex, then certain models cannot provide easy answer, right? So, and it's quite often that one becomes so involved with the model and the solution that he or she forget that it is a model, not the actual system that you analyze. So, I often happen to see several people, including several students in the conference. Yeah. They, for example, they use certain models, okay, say linear model, and then they thought this is correct because the result seems like very nice. But this is actually not the correct solution, but they still insist on using that, even though the assumption has been violated. Okay? So, for example, if you assume it is a linear model, then the assumption must be linear, right? But the assumption is not linear, then you should not insist to use that assumption. So, but they really insist to use assumption, the assumption of linearity. So this is a problem. Okay. So a good model and its solution may represent a good approximation of the solution to the actual system, but it is not the solution to the actual system. So remember, model is just approximation. Okay. Don't get too deep into the actual model that you believe that this is to be true. Remember, all models are wrong, right? But some are useful. So it is a misconception that a larger or more complex or sophisticated model will be a better model. So the reality is the other way around. Yeah? So I think Occam Razor said that if you have equally good hypothesis, you will select the simpler one. Okay? So do not force the problem to fit a particular model type. Say you are using linear programming, right? Because you are familiar with it, because you already learned about it. And then you insist to use linear programming, even though the actual model is not linear, for example. So often that one becomes so enthralled with one type of model that he or she tried to place every problem into that format. Oh, what is the consequence of wrong prediction? So that depends on the context, right? So for example, simple prediction like the food in the refrigerator, what is the expiry date? You miss predict that, then the food become rotten. Then you will get sick, right? So, when I was in Japan, okay, there is a law in Japan that every 8 hours, every food that they sell must be thrown away at 8 hours. For example, in 7-Eleven, in Family Mart, right? So then they need to throw away the food that is already 8 hours, expired already. The food is still very good, 8 hours. They put in the ref. But because of the law, right, then they need to throw it away. That's why if you go to Japan, you will not see any beggar there. There is no beggar in Japan. Why? Homeless many, but no beggar. Why? Because every 8 hours they will queue in the supermarket. Right? They will get the food for free. Because those free food are thrown away. The same thing in the night, for example. Before closing, they will also throw all the food. Yeah. Cooked food, they will throw. So, in that case, you will see that their science of prediction become very crucial for them. Of course, no company will give away the food, okay, for easily, right? So they need to predict very accurate so that they will not waste. It's not the intention of the company to give to the poor, right? So they want to make profit. Okay? But at the same time, because of the law, they need to throw it away. So then they need to predict the customer's behavior, okay, accurately. At the same time, okay, so if, for example, during the event, okay, there is an event nearby, they will predict also accurately based on several years. How many should they provide all this food? Okay. So during the event, you will go to, say for example, 7-Eleven. There are plenty of food. Okay. You always have food that you can buy there. So prediction is very important in that case, right? Now, if they have too much inventory, then it will create unnecessary storage cost also. Okay. In Metro Manila, okay, to go from one place to another is required just 5 kilometers required around 2 hours, 1.5 hours to 2 hours. So going to work there is like normally 4 hours a day. Going 2 hours, go home is 2 hours. So traffic congestion become very crucial that you can predict. Right? In here, you go to work or school just half hour, you complain already. But there, it's normal. Some of my students can take like 8 hours just to travel to campus. Using both, because they come from another province. Right? So, KIGO, yeah, garbage in, garbage out. So wrong data will lead to wrong result. Okay. Again, outlier is also a problem, right? So And if you have data, sometimes you cannot get all data. How about the missing values? How do you handle missing values in the data? Anyone can suggest? How do you handle missing values? Say you have data, collected data, and then, say questionnaire. Okay? Certain respondent did not answer that question. Will you throw the whole questionnaire for that respondent? Or you will impute? What do you think?
Can we assume it?
Yes, you can assume for each variable, you can assume the same as the median. Okay, so you can impute that. Because when you use a median, not mean, not average, median. Okay. Then basically the central tendency will be equal to the whole data set anyway. So your whole data set does not change. Right? And data cleaning. Okay? So, or you don't need to impute the missing values. That means you just put an A. Okay? In the coding, usually I put -9. Negative mean is not correct data. So I'll put -9. So, or -999. That means missing values. Right? So if you use, for example, SPSS or other statistical software, so you specify this is missing values. You code it as a missing value. Then it will not be analyzed for that variable. Okay. And data cleaning. Okay. So you clean the data before you analyze. It's very important because otherwise, if your data is, for example, mistype, okay, they actually the same data, but you mistype, then you interpret it as different data, but actually the same data. So in this case, you need to clean the data. So how do you know that this is mistake? One way is to check the outlier. Okay, the outlier means this is the data that is not usually. For example, the data is 2, 3, 4. Suddenly you have 300. Right? Oh, maybe they mistype, adding 0. By checking the outlier, that data that is not usual, then you will know, oh, this is probably missing. Then you check again. For example, in the questionnaire, you will check again the questionnaire. Oh, I mistyped this. Okay, the original data you check. Okay. Without checking, without cleaning, you just analyze, you will get wrong result. The same thing is not just the data, also the feature. The feature means the variables. So if you are dealing with certain field, certain domain, okay, there is need for domain knowledge, right? Say you're dealing with health, so probably you will bring some health expert to deal with this. Okay, so if you are, say, doing some consultation about biology, for example, then you bring in biologists. So they are the domain expert. Okay? So the domain expert will tell you, okay, which feature that is plausible, which feature that is actually workable, feasible. Okay? And then we also don't want 2 or 3 variables with high correlation in the same model. Okay? We don't want 2 or more variables that correlated in the same model. Why? Why we don't want that? Say, give example of correlated variables. Can you give example of correlated variables? Say, you have the price is actually equal to revenue minus cost, right? Okay, so revenue and cost is independent, but the price and the revenue and the cost is correlated because price is equal revenue minus cost. So you don't want to put price and revenue and cost together in one model. Okay? Either you use price and revenue or price and cost or revenue and cost, but not the three of them. Because they are correlated. Okay? Redundant. So what happens if you put, if you don't know and you insist, or you know but you insist. So if you don't know, you check the correlation first, right? And then, oh, they are correlated, then you remove. But now you know they are correlated, but you insist, what will happen? When you include the same or correlated variable in the same model, okay, the result, the accuracy will become very high. This is how you cheat. But at the same time, this model means nothing because actually it's wrong model. Okay, so it's a wrong model assumption. In fact, if you check all the models, usually they will call this IID. If you read some books, they will write it as IID. What does IID mean? Independent identical distribution. It must be independent, right? So cannot be correlated. Oh, back to my story earlier. So what is my input parameter model and output? So here the input was my age, right? My grandma's age. This is a children's story. So my parameter was my working age, right? And then the model was just simple model of projection of age difference. Okay. The output will be the grandma's age 15 years later, right? So, and then there is a threshold, right? What is the threshold? Oh, there is a threshold of life expectancy with the statistics, and there is a decision in here. What? Well, if the life beyond expectancy, then the decision is you probably die already, grandma. This is another example of using very simple model to predict. We predict, in fact, this is used already. In the Philippines, there is a Mall of Asia, MOA. It has very huge, okay, it's about 3 kilometers, the mall. The mall is very big. Okay. This is like the largest mall in Asia. You look at the square meter, 4.3 million square feet. Okay, and how they predict that? Why they make that kind of very big mall? Because they use this trip rate. Okay, the trip rate for shopping mall is 45.65 pedestrian per 1,000 square feet. This is their assumption, so this is the invariance. Okay. Then based on this trip rate that this is from another study, right? So based on this trip rate, okay, when they input that value, they can predict the demand must be around 200,000 foot traffic daily. That means around 200,000 people will enter that mall every day. Okay. So this is a simple constant proportion in predicting. And this this kind of simple model has been used in economic, in marketing, right? For example, or you see on the street, right? In the street, usually you see advertisement, right? Advertising. Okay. So how they calculate that advertising? They usually based on the traffic, right? They count the traffic on that road, for example, Raya Darmo in Surabaya. Okay. So you can check the number of traffic there, right? And then based on the traffic, they will say certain percentage of this traffic will look at that advertising. And very simple constant proportion here. And then they say this is the revenue that you will get estimated. Okay. Now, here is the problem with the average. So I have this data, 2, 3, 4, 2, 3, 4, 2, 3, and then the last one is 2, 3, 2. Clearly, the last data is an outlier, right? Because all the other data is 2, 3, and 4, except the last data. Now, what happens if you calculate all of this? Okay, you use Excel, you calculate all of this. Okay, what is the average? What is the mean? Okay, the mean means you sum all of this divided by the number of data, right? So then you will get 28.3, but the median is still 3. Okay, so in that case, we know that the arithmetic means is sensitive to outlier. If you have just one outlier, it will pull the average to the outlier. Okay? While the median is actually robust central tendency that we can use instead of mean. So my suggestion is use median, don't use mean. Don't use average as much as possible. Not always possible, but as much as possible. Okay, another way to predict. Yeah, again, I just use a very simple model here. Say, I want to predict today's price is 10. Oh no, in 2008 was 10. In 2018, at that time was present, so 15. Okay. They want to predict the future, which is 2028. So how do you predict the future only with two numbers? How do you predict the future with only the two numbers, which is 10 and 15? Right? So what is the model? Or simple? Because you have only 2 points. If you have only 1 point, you cannot predict, right? If you have 2 points, at least you can predict this one. How to predict? Oh, you know the difference is 10, the time difference is 10, right? Then the price difference is 5, yeah? 5 million in this case. So in that case, you can just say, look, in that case, 10 years from now, which is 2028 in that case, yeah? It will become 20, right? Easy. You just repeat the same thing. Okay. 10 to 15 increase 5, so then the next one must be the same increase. Then you will ask, how do you know it's the same increase? Well, it's invariant, so it's assumption. Right? So you dare to assume. In modeling, you dare to assume. But you also remember that the assumption is the one that make your model vulnerable, right? The weak point of the model is actually on the assumption itself. So if your assumption is wrong, the model is wrong, your prediction is wrong. Right. Okay. So again, I use linear regression as simple. You learned this, right? Simple linear regression. You took statistic already. Which one is the error? The left or the right? Forget the left. Yeah. So the one that you learn in the usual statistic is the left side, with the simple linear regression, right? The error is vertical. Yeah. But what happens if your model is actually vertical? It's possible? Yes, it's possible, right? How if your model is actually vertical? Then the error become infinity. So, so this is not, so in fact, simple linear regression is simple using mean, okay, based on normal distribution, but this is not robust. Okay, the right side here, this is actually robust linear regression. This is sometimes called orthogonal. Why? Because the error must be orthogonal, perpendicular to the model. Of course, computationally is more complex, okay? But at the same time, this is more correct. For example, if your model is actually vertical, orthogonal linear regression still can do, okay? While the simple linear regression cannot do. Now, talking about the assumption, so what is the assumption of regression? You learned this before. Did the teacher tell you the assumption of simple linear regression? No? or they just tell you that how do you calculate that? And then you are very satisfied. Oh, I can already calculate the model. Yay. No, now you grow up, okay? You get more mature right now. So you know model is nothing. Most important is actually the assumption, the invariance. Right? So it is the invariant, knowing the weakness become your strength. Okay? If you don't know your own weakness, then you don't know your own strength, right? The same thing with the regression here. Okay? It's assumed to be linear. Okay? If your model is not linear, like down left here, it's not linear, then you cannot use linear regression. You must use nonlinear regression. Right? Second assumption is constant variance. Okay? In linear regression, there is an assumption of constant variance. They assume the variance must be constant. How about in the right side here? You see right down drawing, you see? This is the variance is not constant. In fact, this is not distributed, it's not normal distributed also. Right? The third assumption is normal distributed. So if you have the model like this on the right side here, okay, you cannot use simple linear regression. You use other model that that don't have that assumption of simple linear regression. Okay? So how do you know? And the question is, how do you know that this model is actually linear, constant variance, normal distribution? The assumption. If you go to Excel and you run the simple linear regression, have you ever tried? Oh, let's try. Let's open your Excel, okay? And you can create random data. So X Y. You can create any random data. Say 1, 2, 3, 4, 5. I have 10, 12, 15, 18, 21. Okay. So how do you do regression in Excel? I need data analysis. Oh, I need to share my screen, right? Oh, there is no data analysis. Wait. If you don't have data analysis, you go to the file, option, add-ins, okay, and go, and then here you check the analysis toolpath. Okay, this one, analysis toolpath. There, you have data analysis here. Can you see it? Then you can go regression. Here regression, click OK. So this is the Y, this is the X, right? And the first row is labeled, right? Here it is. This is the one that you need to check, yeah? Residual, standardized, standardized plot, lean fit, and normal distribution plot. Why you Excel already have this? Why? Because this is the one that to check whether the assumption, okay, of normal distribution, linear, and what do you call that? Linear assumption, normal distribution, and earlier constant variance, okay, is checked there. So click OK. There you get it. Right? So this is the plot. Oh, there's an outlier here. Right? The residual plot will show you. Okay? So there is an outlier here. Of course, my data is too small, so you cannot see well. It's only 5. But this is how you get. So in linear regression, you will check the R square here, right? This is your coefficient. This is the slope. This is the intercept. And you will check the T statistic must be larger than 1.645, and then the F must be less than 0.05. And this is the residual. Okay. So back to the slide. Did you try in Excel? So using the plot of the residual here, what is the meaning of residual? Residual is the error, huh? The observed minus the predicted. Okay. Using the plot of the residual, then you can check. Okay. Good residual will be symmetric, center at 0 with no pattern. That is a good residual. Okay. Bad residual, okay, you can see that they are not normal, or the variance become bigger, okay, or non-linear, something like this, or multimodal. So there are several category, okay, or there is outlier. So from the residual you will know, right? And when the variance is not constant, this is called heteroscedasticity. So in that case, you will use a weighted regression or orthogonal regression. You will not use simple linear regression. Oh, until here first. Is there any question you want? Did you try, or you want to ask any question about it? It's okay? You can plot the residual, right? No problem. Good. Next, I want to discuss with you about policy variable. What is policy variable? Policy variable is variable that you will use for your decision. Other variables is non-policy variables are the variables that, well, it's good to be there, but if not, that is fine. Okay, let's give example. Say you want to buy a car. What is the variable that you will use to select the car?
Price.
Price. Okay, that's policy variable. What else? Is color important for you?
Could be.
Could be. So then if it is important for you, could be, then it's probably other variable. So the price is okay, but the color is not okay. Will you buy it?
Yeah.
Yeah, then is the color is not policy variable,
Oh.
right?
So policy variables are variables that are significant.
Correct. Correct. So policy variable is the variable that will surely make you create decision. Other variable is good to be there. It's not is okay, right? Clear. So if you want to decide who will be your boyfriend, what is the variables? Policy variables. Probably the look. What else?
I have a question. Can we have like multiple policy variables?
Of course, you will have many.
Oh, okay.
Okay, so what else? Aside from the look, probably you will have gender is sure, right? So, the age probably. Okay, the age different, right? What else? The wealth important. It's good to be there, but it's not decision. Then it's other variable, non-policy, right? So what else? So with this example, is it clear what is policy variable and not clear? Not policy. Okay. So back to the slide. What you need to predict is the policy variables. Okay. And usually, policy variable is variable that is state, discrete. So in that case, probably you want to use logistic model rather than linear regression, right? So the model influenced by the data type also. So here is another example of what is called multiple linear regression. So in this example, okay, I'm using the jargon of machine learning here, right? So it's actually multiple linear regression. What is the data here? The data is only two. The age of the car and the kilometer of the car. This is used car, right? And these are the price, okay? So in machine learning, there is what is called teacher. Okay? There's no student, only teacher. And there is a learning algorithm. Okay? So basically the model. Okay? And there is a system here, which is in this case a multiple linear regression. And the parameters are three, right? A, B, and C. Okay? So the age here represents the number of months of the car. For example, 2 months car and 4,200 kilometer, the price is 800 something thousand or million. Okay. So my question to you is this. What is the meaning of A, B, and C? what is the sign? What are the signs? How do you interpret this? Is the sign negative 24 correct? If the sign of A is positive, 900,000 correct? How do you know? Remember, it is you as human who interpret, who verify the model. Okay? You can have the data, put it into computer, you get this value, right? The parameter, correct? But your job is not just to input the data into the computer and that get the result. That is the job of the machine. It's not your job. Okay? Your job is to interpret this. Okay? What is the meaning? How do you get the meaning? Easy. Look at this. What happens if the age and kilometer I put 0? What is the meaning of a car with age 0 and kilometer 0? Devi, if car with 0 kilometer, 0 age, what's that mean?
Haven't been used. Right?
Yes, it hasn't been used. That means a new car. Right? So, look at the model here. If age is 0, kilometer is 0, price equal?
20,000
Yes,
equals A.
equal A. Yeah? A is 900,000. Here is multiplied.
100,000. Yeah.
So it's 900 million. That is the price of the new car of that type. Right? So, how about this B? What is the meaning of B in here?
For every increase of age, the car
Yes.
value decreased by
Very
minus
good.
20.
Decrease by. Right? Decrease by, that's why the value, the sign must be negative. From the meaning, you know that the sign must be negative. If the sign is positive, something is wrong. Then you check, oh, probably I mistyped certain data, maybe I make a wrong model. You know. You got it. Don't just input the data into the computer without understanding. Right? But how do you understand this? Of course, you will understand this because you know the meaning. How do you know the meaning? You must be the expert in this case, right? At least you know that this is the price of car, that this is B must be reduction, decrease of the price. Meaning that you have experience or at least hear about it, right? Otherwise, say you are a child who never know about anything about car, will you able to tell that this is the decrease? No, right? You got it. Okay, so you need to check the meaning, you check the sign, okay, and actually you can also check the value, the range of the value. Okay, common sense or not, make sense or not. If it doesn't make sense, okay, something is wrong with the model or the data. Okay, here is the suggestion. Say, for example, we use regression, right? A while ago, I showed the R square must be larger than 0.8, right? The F test must be less than 0.05, okay? The T test must be larger than 1.645. This value are rule of thumbs, right? But this can be checked using computer. Okay. Now, the table below is very important. You check first, what variable is this? Okay. If this is variable in policy variable, okay, and the sign is correct, and the significance of t-test is correct, then of course you must include, right? This variable you will include, okay? But what will happen if, okay, the sign is correct, is policy variable, but the t-test say this is not significant, meaning the value of the t is less than 1.645, okay, the absolute value. Then you will say, well, if it is policy variable, I will include, but if it is other variable, I will just reject this. I will not include this variable into the model, right? How about if it is wrong sign? Okay, if it is wrong sign and this is other variable, not policy variable, you simply reject, right? But if it is wrong sign, okay, and not significant, it is a problem. But you know, this is not significant. That means this policy probably not so important. Okay? But if it is wrong sign and it is significant, meaning significant means the t-test is larger than 1.645, right? Then you have a big problem there. So in that case, you probably want to change the model or check the data. Okay, so this is the guideline. These are the assumption of multiple linear regression. So linear relationship, multivariate normality, multicollinearity, and homoscedasticity, meaning the variance is constant again. Okay. Okay. Anyway, so those are the guideline, okay, that I use for linear regression. Now I have a function approximation here. So I have this data, okay, with certain outlier little here. So my question to you, which line is the best? The black line, the blue line, the red line, or the green line for the function approximation of those data? What do you think? The four of them are a model for this data, right? Given the data, I can create different models. Okay. The black line is linear, the blue line, red, and green line are non-linear. So which one is better? Joy.
Blue line.
The red one? You will choose the red one?
The blue one.
The blue one, why?
That's the closest to the line.
Mm-hmm. How about you, Livy? Which one you will choose? The blue one, the black one, the red one. Look, the red one is passing all the points. Eh? But the green one is also passing all the points. Joy said the blue one. How about you, Livy? Which one you will choose?
Probably the red one.
Why the red one? No reason.
It's passing through.
It's passed through all the points. But the green one is also passed through the points. Okay, so the answer is correct, Joy. Yeah? The blue one is the best. Okay? The black one does not count the point here, the point in the almost outlier here. Okay? But the red one passing all the points, that means this is interpolation. Okay? So it's overfit. Meaning, within this scope of data, yes, it can interpolate, but it cannot extrapolate. It cannot go beyond this data. So if you have new data in, okay, so the blue one can approximate, right? The black one can approximate, but the red one approximation will be wrong. Okay? The same thing with the green one here. So it's overfit. Okay? In fact, we don't like the line that passed through all the data. Okay? It's tend to be overfit. Overfit means you cannot generalize. You can only use for the data that you calibrate in. See? It's good calibration, but very bad in validation. Very bad in prediction. Okay? It's only good for the data that you put it in. So that is called overfit. We don't like that. Because our goal in the in modeling is actually to predict, to control, not just to get the model. Okay. Yeah, this is the Occam razor. So if if you have two theories explain the fact equally well, then the simpler theory will be preferred. So in that case, the blue one is best. So in classification, okay, this is another example of classification. You want to get whether this is a conveyor belt, okay, and then the fishes are passing through the conveyor belt. We want to know whether this is salmon or sea bass. Okay. So then what happens is you check, okay, based on the data you get the distribution, right? From the distribution, say distribution of the length of the fish, fish length. So you see here the distribution have a lot of things in common. The overlapping between the two distributions is very big. And then you check, oh, maybe I will find another feature. In that case, this feature is lightness, right? So the overlapping is actually less. Then you said, how about if I combine the two features? Okay, so the width and the lightness of the color. Then you can get better classifier here. Now, which classifier should I use? Is a line, okay, or should I use this line? This one have no error in misclassification, nothing. But again, this is overfit, right? So probably you will get the middle part. It is non-linear with less error. Okay, this is probably the optimum one. Okay, so this is how you trade off the model. You have many different choices of model, then you start to see which model should I use. Okay, this is just an introduction. At least you get the idea. Okay, during this course you will see a lot of models. Okay, later on, then you may ask which one, or you make a trade-off. Yeah, which model you will use. Okay, so this is just a joke. So if you have all the points, you get the knowledge. Yeah? If you connect the dots, you get the experience. Okay, but if you create a cut here, then you have actually an overfitting, right? Okay. Okay, so this is like the summary. Okay, so using the model without understanding of the assumption behind will create a curse for you, a stigma, right? Proud of a lot of big data without the cleaning is also problematic. And if you're too dependent on the performance criteria without understanding the meaning of the data and the result, without interpreting, then it will create a curse for you, a stigma for you. Okay? So always remember, use your common sense. Okay? If you have no common sense based on just the result of a computer, this is very bad. Okay? Correlated variables earlier. Yeah? So don't use correlated variable in one model. And the last one is, of course, a generalization issue. Yeah? Don't make your model overfit. Okay? Okay, so come back to the earlier. So if you want to understand the model, test your assumption. Okay? Check the distribution, do data cleaning, and when you apply the model, okay, remember you do three things. First is to calibrate. Okay? Second is to validate. Yeah? And the last one is use your common sense to verify, okay, whether your model is correct or not. Okay, so I think until here today. Thank you very much for your attention. Is there any question?
No, it's not clear.
Everything okay?
Yeah, everything okay.
Okay. So next meeting, we will discuss about calculus. Okay. So calculus-based optimization. Can you read beforehand? My question to you first. Do you okay. Did you learn calculus?
Yeah, up till calculus 2.
Okay. That is fine. That means integration is fine, right?
Yeah, hopefully.
So second order derivation is okay.
Yes.
Okay, great. Wow, very good. Okay. Okay. So thank you very much.
Okay, thank you, sir. See you next week.
See you.
Yes, sir.